very warm welcome. We are talking about solid state in this series on NCERT. We are discussing NCERT and I present to you solid state. This is Shishir Mittal from Vyas EDIFICATION. Let's begin. Define the term amorphous. Give a few examples of amorphous solids. What exactly is amorphous? Whenever solid substance is there in which individual particles have no systematic order. No systematic order means none of them must be ordered. Actually, they could be ordered for a short range. It is not necessary. They may be, they may not be. But at least long range order must not be there. If that is the case, then these are called amorphous solids. So amorphous, as you can see, amorphous means no form. They have no systematic crystal structure. So particles of irregular shape. I mean, that's not very true. I would say rather particles of irregular arrangement, because they all could be having identical shape and that is also perfectly okay. Irregular arrangement. Could I not have corrected this before writing it? I could have. This is an intentional gap so that I can highlight that these are the common errors made by people, and especially the students. The arrangement of constituent particles in such a solid has only short range order. This is also a kind of misconception. It kind of makes it very necessary that there has to be short range order. No. The truth is they may or may not have any order. If they are totally disordered, they are amorphous. Even if they have short range order, don't start calling it that they are ordered, they are ordered. They are not ordered, they are still amorphous. They will be crystalline only if there is a long range order. There may be a short range order. It's not compulsory, it is optional, right? In such an arrangement, a regular and periodically repeating pattern is observed over short distances only. May be observed. What I'm giving you is a very popular answer, the way it is written, and why I'm modifying it, because that should be the answer, right? So I hope you get this. Examples are very common. If you take a plastic, if you take rubber, if you take glass, they're classical amorphous materials. If you want point-by-point comparison between crystalline and amorphous solids, well, this is what we have. You could talk about the shape, melting points, cleavage property, enthalpy of fusion, isotropic nature or anisotropic nature, and arrangement of constituent particles. These are various points on which you can compare crystalline and amorphous. Like crystalline solids have a very well-defined geometrical shape. Amorphous may not have that, right? But please remember, individual particle, if it is very regularly shaped, still the overall solid may be amorphous only because the arrangement in which those particles are there may not be very regular. Sharp melting points for crystalline solids. Amorphous solids have a range of melting points. They don't have a sharp melting point. That is the most characteristic defining property or distinction between crystalline and amorphous. And if you're trying to cut crystalline solids with a sharp tool, imagine taking a sugar crystal and you're trying to cut it with a knife. No, you would find it is difficult to cut, and if you break it, if you hammer it, it cleaves around plain irregular surfaces. I mean, it's not, you can't just shape it like, if you're carving with a knife, if you're, say, for example, carving wood with knife or you're carving plastic with a knife, you would find that you can carve it in whichever shape you want. In crystalline, because they're amorphous, in crystalline solids, you can cut it slightly, but the moment you make a small cut, the remaining portion breaks away on its own, giving you a plain surface. And that is which makes carving on these solids a little more difficult when they are crystalline. Enthalpy of fusion, if they have sharp melting point, they have well-defined enthalpies of fusion. Amorphous solids don't have sharp melting points, so obviously they would not have well-defined enthalpies of fusion. They could, they could take different heats in melting, kind of. Anisotropic. Crystalline solids are anisotropic. That means all their properties, if any property at a given point is measured in different directions, you find that that property, depending upon direction, could be different. Even if a single property exists, which at a given point, if it is measured in this direction or this or that, is different, you would find that the solid is called anisotropic. Isotropic solids, they have all similar properties. That's the case. I mean, the properties, whichever property you try to measure, in one direction, in second, third direction, the property will be measured to be same. Sometimes crystalline solids are called true solids, amorphous solids are called pseudo-solids. Even supercooled liquids is a very fancy name which is given to amorphous solids because they don't have a long range order. So they may not have an order or they may have a short range order, while crystalline solids always have a long range order. These are so many points of distinctions between crystalline and amorphous solids. What makes glass different from a solid such as quartz? Under what conditions would quartz be converted into glass? Quartz is a very pure form of silicon dioxide or silica. So quartz is SiO2, silica. And this is beautiful crystalline structure. Very good looking, transparent, brilliant crystals of quartz are available. Now, if you wish to convert this to glass, now glass is an amorphous solid which is also called supercooled liquid. So can we convert quartz to glass? Well, it is difficult but not impossible. What you do is you heat quartz desperately. Heat it to such an extent that, it comes close to its melting point. And then suddenly quench it. Quenching means sudden cooling. Cool it suddenly. So heat, then quench. And heating is not that you keep it in sun. Heat it very strongly, bring it close to its melting point, and then suddenly cool it so that you have an abrupt crystal structure frozen. And that would be glass, the supercooled liquid. That's it. That's the way to do it. Classify each of the following solids as ionic, metallic, molecular, covalent network or amorphous. Please note, first, ionic, metallic, molecular or network covalent solids are crystalline solids. So you have to distinguish between crystalline and amorphous. If crystalline, which type of crystalline? Because there are 4 types: ionic, covalent, metallic, and molecular solids, of course. So let's take a look. P4O10. Now P4O10 is a molecule. So this will be a molecular crystalline solid. You might ask, how do I know it is going to be crystalline? Actually, everything is crystalline. Unless you have long polymers or you have strange structures which you mug up as amorphous, you assume it is crystalline, it works always. Ammonium phosphate, now this has ions. It has NH4 plus ions, it has PO4 3 minus ions. So it's an ionic crystalline solid. SiC, silicon carbide, also called carborundum. It is a diamond-like structure. Very beautiful network solid. It's a covalent network solid. It's a covalent network solid. Just like diamond, it's an infinite structure. Iodine is a molecular solid. You have small molecules of iodine. Iodine is a molecular solid. P4 is again a molecular solid because you have tetrahedral units of phosphorus like this. And they're neatly packed in a crystalline structure. Yes, it is again a molecular solid. Plastic. Now, NCERT would say plastic is amorphous. If you Google this and read more about this, you would discover that now even crystalline plastics are available. So there are 2 types of plastics, crystalline and amorphous, but usually, the old answer is that they are amorphous, and NCERT is really an ancient book like dinosaurs, so they just talk about amorphous. So this would be amorphous. Graphite. Graphite is a beautiful crystalline solid and it is a covalent network solid. It has an infinite structure, hexagonal sheet structure which is infinite and joined by covalent bonds. It is a covalent network solid. Brass is a metal, it's an alloy, so it is a metallic solid. Metallic has appeared for the first time, yes, it's a metallic solid. Rubidium is a metallic solid. Lithium bromide is an ionic solid, and silicon again is a covalent network solid. Don't forget, silicon itself has a diamond-like structure. It's a covalent network solid. What is meant by the term coordination number? The number of nearest neighbors to any atom, molecule or ion in a crystalline structure is called the coordination number of that atom, molecule or ion. So what is coordination number? It is the number of nearest neighbors, or the number of particles which surround a given particle or which are in immediate contact with a given particle are called its nearest neighbors, or their number is called the coordination number. And then there is a second part to the question. It says, what is the coordination number of atoms in a cubic close packed structure? If you consider 3 layers of cubic close packed structure, you will find top layer, middle layer, bottom layer. If this is the atom, if this is the central atom, there are 1, 2, 3, 4, 5, 6. If there are 6 atoms surrounding it, 3 on top and 3 on bottom. So 6 plus 3 plus 3, how much does that make? That makes it 12. Yes, that would be 12. Yes, that would be 12. In a body-centered cubic structure. Now, what would be a body-centered cubic structure? Oh my God, this is a body-centered cubic structure? Yes. So, if this is the center, then 1, 2, 3, 4, 5, 6, 7, 8. There are 8 spheres surrounding it at the corners of a cube. So, naturally, the coordination number is 8. This is 12 and this is 8. Done? Done. How can you know the atomic mass of an unknown metal if you know its density and the dimension of its unit cell? Explain. The lovely NCERT stuff. They've eaten away one part. Truth is, you cannot determine the atomic mass from only this. You also need to have an additional information. What is the crystal structure? Or how many atoms or how many units are present within a given unit cell. But assuming this is standard NCERT style, let's not ruin it too much. So the way we do it is this. See, density by nature is called mass by volume, right? Now, we can use this formula for unit cell also. Density of a given substance is same as density of its unit cell if it is crystalline. And a unit cell, that means mass of unit cell divided by volume of unit cell. Now, what is mass of unit cell? Now, mass of unit cell would be, we say it is Z into atomic mass by Na. What is this? Atomic mass is mass of 1 mole of atoms. So divided by Na would give you the mass of a single atom. So this is the mass of a single atom, and Z is number of atoms in a unit cell. For example, in simple cubic structure, Z is equal to 1. In BCC, Z is equal to 2. In FCC, Z is equal to 4. So there are different cases, right? But we can figure out, once we know what is the crystal structure, we get the value of Z. So this is the mass of atoms present in one unit cell divided by volume of one unit cell, and I am writing A cube because I am assuming this is a cubic unit cell. It could have been hexagonal. In this case, the formula would have changed. Mass by volume is the same, but A cube, Now, volume of hexagon is not A cube, obviously. This is only the volume of cube, where A is the edge length. A is the edge length. You could say that, is this applicable only for cubic? Well, even if it is hexagonal, I'm sure, see, I'm given dimension of its unit cell. If I know the dimensions of unit cell, I can always find out the volume. I can divide by volume. That is not a problem. So I know the volume. I'm given the volume. I am also given the density. So if I'm given density and volume, can I not find the mass of a unit cell? So I am getting the mass of a unit cell as its volume into density. And this is also equal to Z into A upon NA. I know this, I know this, I know Avogadro's number. So can I determine atomic mass A? Yes, but there is a small catch. You should know Z. Z has not been mentioned in NCERT question, but this being NCERT, we are open to some modifications because they leave out and eat away half the data, which is okay. So they have assumed that we know Z. If we don't know Z, then you won't be able to find. So we have to know Z, but assuming that since we know the dimensions of unit cell, maybe we also, there's no logic, but we should also be knowing Z, the nature of crystal structure. If we have this information from this formula, we can substitute and find the value of atomic mass. That's it. Stability of a crystal is reflected in the magnitude of its melting points. Comment. Collect melting points of solid water, ethanol, diethyl ether and methane from a data book. What can you say about the intermolecular forces between these molecules? Now, first of all, why is it that a solid should be a solid? A solid is a solid only because its particles attract each other. And that force of attraction is so substantial that it binds the solid particles together, maybe atoms, maybe molecules, maybe ions. And since they stay very close to each other, they can only vibrate, they're not able to move away from each other. And that is why a solid remains a solid. So obviously, greater the intermolecular forces of attraction, greater is the force which is actually binding the solid particles together, greater is the stability of a crystal, because if the attraction is more, crystal will be more stable. And naturally, if it is more stable, the crystal will melt or the crystal will break away only at a higher temperature. The higher the forces of attraction, higher is the stability of crystal and higher is the melting point by basic chemical common sense. Now, we were supposed to comment, we have commented. Melting point data we are supposed to collect. So let me present to you the melting point data of ice, which is 0 degrees Celsius or 273 Kelvin. Now, please appreciate that ice has a beautiful case of hydrogen bonding. And each water molecule actually forms 4 hydrogen bonds. So ice is a very well connected hydrogen bonded structure. Strong hydrogen bonds, each molecule forming 4 hydrogen bonds. Then you have ethyl alcohol. Now ethyl alcohol is EtOH, lovely though it is. But in ethyl alcohol, you find, my dear, that only 2 hydrogen bonds are present per molecule. So since this ethyl group is hydrophobic, it does not participate in any hydrogen bonding, the number of hydrogen bondings is reduced. In water molecule, there were 4 hydrogen bonds per molecule. In ethanol, there are only 2 hydrogen bonds per molecule. So naturally, the strength of intermolecular attraction is reduced. And because the strength of intermolecular attraction is reduced, the melting point reduces from 273 Kelvin to barely 158.5 Kelvin, which is significantly less, more than 100 degrees, 100 Kelvin lesser, around 120 Kelvin lesser, because attraction is much less. Fine. Diethyl ether appears to be very close, but you must appreciate, see again, NCERT being NCERT, this is not a very fair comparison. Why? Because ethanol is CH3, CH2OH. A very good comparison should have been dimethyl ether. Maybe it is a printing error or somebody who was finally editing it became a little extra intelligent and ethyl they matched without realizing that this has only 2 carbons while this would have 4 carbons. Now diethyl ether is a polar molecule and it has no hydrogen bonds. It is a polar molecule with no hydrogen bonds, but because it is more massive, instead of 2 carbons, it has 4 carbons. It still has a melting point which is close to ethanol. A little less, but close. Honestly, had it been dimethyl ether, CH3OCH3, which is actually an isomer of ethyl alcohol, and that has a melting point of 132 Kelvin, which again is at least 26 Kelvin lesser as compared to alcohol. This would have been a more clean or a fair comparison. That see, in this case there is hydrogen bonding, and in this case there is no hydrogen bonding, and they are isomers, and melting point substantially comes down. But NCERT has mentioned to take diethyl ether. I took this for the sake of chemistry. But then for sake of NCERT, look at this also. You can say that, well, H bonding is gone, so melting point comes down, but molar mass is now nearly double. If molar mass is higher, that should increase melting point. So even after nearly doubling the molar mass, you have still melting point which is very close, still slightly less, only because hydrogen bonding is no longer there. Still, there is an advantage. What? Because of oxygen, ethers are polar molecule. There is dipole-dipole attraction. If you take a strictly non-polar molecule like methane, melting point drops down to barely 89 Kelvin. That's very cold, very, very cold. Close to minus 200 degrees Celsius. A little more, but I mean, whatever. So you could see that when even permanent dipole attraction is not there, only van der Waals forces or London forces are there, methane has a much lesser melting point because again methane is a non-polar molecule. So hydrogen bonding, less hydrogen bonding, no hydrogen bonding but dipole moment, and even no dipole moment, you find that melting point consistently decreases and the stability of crystal structure also becomes less because of lesser intermolecular forces of attraction. I hope you have understood this very beautiful comparison. Explain how would you compare between hexagonal close packing and cubic close packing. We are supposed to compare HCP with CCP. And whenever you are asked to compare, usually it's a 2-mark question. So you are expected to give at least 4 points. Not at least exactly 4 points. Don't give more, otherwise they'll cut marks. First point is, it has hexagonal unit cell and it has a cubic unit cell. The shape of unit cell is different. Yes, the shape of unit cell is very, very different. Yes. And then, how many molecules, how many atoms or how many spheres are within a unit cell? So Z is equal to 6 or 6 spheres are present. 6 spheres or lattice points or entities in one hexagonal unit cell, and in this case only 4 spheres, atoms in one unit cell. Anything else? Yes, it represents AB, AB, AB type of packing. But the alternate layers are identical, and this represents ABC, ABC, ABC type of packing. If you forget this, I'll give you a trick. When C comes, here also C comes. When there is no C here, it does not begin with C at least. It could be a trick in case you want to just mug this up. These are some very major differences. When it comes to more points, you could give examples of HCP structure. Some examples of HCP and CCP, yes. Additionally, if you're not interested in giving examples, you could draw their diagrams and show that, see, this is the diagram for HCP and this is a diagram for CCP structure. That also is a very beautiful distinguishing point. So you could do that. I'll just show you. Look at the diagrams. This is a classical breakup of CCP structure, and this is a classical breakup of HCP structure. But then, since it's all a little messy, some examples can be given for HCP, like metallic zinc, metallic magnesium. They belong to HCP. Even graphite gives you an HCP structure. CCP, if you want to get the examples of CCP structures, yes, you can very well get them. CCP structure could be gold, silver, copper metals. They crystallize in CCP structure. So yes, the fourth point could very well be this distinction. Additionally, if you just want to drag on, you could give the volumes of unit cell, etc. That really is not a very great thing to say. This is a good answer. How will you distinguish between crystal lattice and a unit cell? Well, that is very interesting and very simple also. Just look at this. This is, if it carries on indefinitely in this direction, this direction, this direction, all these points collected together, they are called crystal lattice. And unit cell is just one portion. If you repeat unit cell, you get actually a crystal lattice, right? So crystal lattice is the superset and unit cell is the most small or the most elementary subset. That, one is whole and one is a part. That is a very clear cut and a very classic distinction between each of them. So if you want to note this point wise, I can give it point wise to you also. So we have, let me write it for you, crystal lattice and unit cell. How do you distinguish? Let's try. First point, it is infinite. Crystal lattice is like a line. It has no beginning, no ending. It's an infinite concept. And unit cell, it is finite. First point, sorry. Then it is the superset. And second point, unit cell is a subset of crystal lattice. Okay. Anything else? If it is infinite, obviously you can't measure its volume. So you can say its size and volume cannot be estimated and its size and volume can be estimated. If unit cell is periodically repeated in space along crystallographic axis without any rotation or without leaving any gaps, I get a crystal lattice. So using a unit cell and by repeating it, I can generate a crystal lattice. If I have a crystal lattice and if I cut a very small portion, in fact the smallest possible portion of it, I could get a unit cell. Yes. So that is why we said this is a subset and this is the superset. that portion is included there. And as a part of an example, fourth point, you could show this diagram. That this, my dears, is a unit cell. And if I keep on, because practically it is very difficult to keep on making this indefinitely, but then I write it like this. That this expansion continues in all the directions. And this is a crystal lattice. This is the fourth point of distinction, a figure which is very clearly showing what is a crystal lattice and what is a unit cell. How will it distinguish between following pairs of terms, a tetrahedral void and an octahedral void? Now this is a very important question. Why? Because both these voids are very crucial in understanding of solid state. How do we answer this? Let's try to write down the points of distinction. And you must remember these points also very carefully. Tetrahedral void and octahedral void. First of all, it is enclosed between four spheres, entities, and it is enclosed between six spheres, entities. Okay, this is just 4 and this is 6. 4 surrounding spheres must be at the corners of a tetrahedron. And in this case, 6 surrounding spheres must be at the corners of an octahedron. In between the content is the same, you can fill up the same thing. So it is surrounded by, there are 4 particles arranged tetrahedrally and there are 6 particles arranged octahedrally. Okay, anything else? Well, if spheres touch each other, tetrahedral void shortcut is TV, octahedral void shortcut is OV. Size of TV is smaller. And if spheres touch each other, size of OV is bigger. Octahedral voids are bigger and tetrahedral voids are relatively smaller voids, which makes sense. Just 4 and you have 6 particles, so obviously you have more space when surrounded by 6 particles. And how exactly do I get an octahedral void? See, you take 3 particles, arrange them in a triangle, and on the top of that put 1/4 particle. This is how you get a tetrahedral void. This is the method to obtain a tetrahedral void. How do you get, this is the 4th point, please note. And octahedral void, how do you get that? Very stylish. You take 3 particles, arrange them in a triangle just like that. You take 3 more particles, arrange them in the form of an opposite triangle. Like this is a triangle like this, and in this case I get a triangle like this, which is opposite, and put one on the top of the other. You could see one triangle here and the other triangle here. This one is pointing forward, this one is pointing backward. Put one on the top of the other, and the hole between them would be an octahedral void. Wow, that would be the case? Yes, that would be the case. If you want more visualizations, I could give you more diagrams. See, this is a tetrahedral void, and this is an octahedral void, right? But if you have to draw in your notebook, well, I think this is a better diagram. You could draw very clearly this and this and show it. These are the 4 points of distinctions, my dear, between a tetrahedral and an octahedral void. How many lattice points are there in one unit cell of each of the following? Face-centered lattice. Yeah, face-centered cubic. Now, if you have a face-centered cubic structure, just take a look. What does that mean? Well, you have particles on the face, yes, and you have particles here. What are you doing? I'm just drawing a FCC structure for you. Very beautiful. Look, there are corner particles, and the beautiful part is corner particles are not touching each other, but they are touching what you call as the face center. Watch this. Very beautiful FCC structure. Now, could you calculate a few things like each corner contributes how much? See, this is cut along 3 faces, 3 planes. So this is 1/8. And there are 8 corners. This is 1 sphere. Right? And how much is this? If you look at this one, this is half. So, face-centered half into 6 faces, 3 spheres. Is there anything at the center, body center? No. So, total 3 plus 1 is 4. So, 4 lattice points are present within one unit cell in case of FCC structure. Face-centered tetragonal. Is there a difference? Actually, tetragonal means that A is equal to B but not equal to C. A. 2 sides are equal but third is not equal, then we say it is tetragonal. Fine. Fortunately or unfortunately, logics will be very similar to this. If this becomes longer, touching may be a problem, but otherwise every corner only 1/8 will be counted and face centers half will be counted. Occupancy of this also is going to be very much the same. It would be 4. What about body centered? Body centered is another beauty altogether. You have atoms sitting at the corner and then atoms just at the body center. How would it look? Well, you can mug it up also, but let me draw this for you. I repeat, corners may not be able to touch each other, but each of them is touching a body center, the huge entity present at the body center like this. Drawing a sphere is always a pain in 3 dimensions, whatever it looks like. So 1/8 into 8 corners. This is 1 and 1 at body center. This fat one at the body center is entirely within. So 1 plus 1 is 2. So 2 atoms are present within each unit cell if you have a body-centered cubic structure. Let's take them point by point and start covering them. Metallic versus ionic crystals. Now, we will say it like this. Well, I'll write down the distinctions here and similarities because we don't have to write them separately. We will list out the similarities in a separate column. Let's try to write down as many as we can. What is similar? Well, both have a regular lattice structure. Both are crystalline, both have regular lattice structure. Of course, that is something which is common between metallic and ionic crystals. Yes. Anything else? A very obvious distinction is that they are bound by metallic bonding, and they are bound by ionic bonds. Then lattice points. And lattice points in metallic crystals are metal atoms. And what happens in metallic bonding? Metal atoms release their electrons, they delocalize them, and they just sit. Electrons are moving around. So all the lattice points have similar positive charge. Electrons which are delocalized, the sea of electrons, that carries the negative charge, but all the lattice points have similar positive charge. And in this case, the lattice points, not all, I would say, the lattice points have positive as well as negative charges. Lattice points have both positive and negative charged particles, because there are cations as well as anions. Since they have delocalized electrons, they conduct electricity in solid state, and they are insulators of electricity, usually in solid state. Why? Because their ions cannot move, they cannot leave their positions, so they can't really conduct the electricity. That makes sense. Anything else? Well, can we talk about malleability, ductility? Yes. Metallic solids are malleable and ductile. They're also sonorous. Malleable, ductile, sonorous. Sonorous means they have a typical bell kind of a sound, a metallic sound of clinking. Ionic crystals don't have that. So they are brittle. If you beat them by hammer, they will just break like glass. You can't draw wires. They are not malleable, not ductile. They are brittle, they are hard, and they are non-sonorous. Take salt crystals and try to crush them, bang them together. You won't actually hear a clinking sound of metal or something. It's just a dull thud, nothing else. So they are brittle, they are hard, and they are non-sonorous. Yes. These are 4 points of distinction. I could give you many more points. Metallic solids are never transparent. Metals are always opaque to visible light. Ionic crystals, there are rare ionic crystals which actually could be transparent, like alums, for example. They could be transparent. Potassium nitrate crystals are lovely transparent crystals. Needle-shaped crystals of lead acetate, ammonium acetate are lovely transparent crystals at times. So they could give you transparent crystals. Their crystals may be transparent to visible light. There are cases, and in none of the metallic solids you would ever find that a metal is ever transparent to visible light. So yes, these are, and you could give examples, metallic solids like iron, cobalt, nickel, gold, any metal. And ionic solids like NaCl, RbCl, KBr, CaSO4, all these are. So I have given you six points of distinction between metallic and ionic solids. Do they have any similarities? Well, they have sharp melting points. They both have sharp melting points. They melt at a unique temperature. Yes, that's very beautiful. Anything common? They both conduct electricity in molten state. If you melt them, a molten metallic substance also will conduct electricity, and a molten ionic crystal also would conduct electricity. Wow. Anything else? Yes, a fourth point. They're usually hard. They're usually hard. A metallic crystal like iron or titanium is hard. I mean, there are cases like mercury or alkali metals which are soft, but if you just leave them out, most of the metallic crystals are pretty hard, and most of the ionic crystals are also pretty hard. So yes, they do have that in common very much. These are 4 points of similarities between metallic and ionic crystals. Explain that ionic solids are hard and brittle. Why should they be hard and why should they be brittle? That's a very beautiful and a very simple explanation. Let me first draw a metallic solid for you. Well, we have cations, 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 cations. Is this what? An ionic solid? Crystal? Well, there are anions also. Let me draw them for you. You have anions, you have anions. What is this? This is cheap time pass. No, no, no. It's a very beautiful thing I'm doing. You should also do the same. Make this in your notebook. Fine. This is an ionic solid. Opposite charges, strong Coulombic attraction. Each cation is surrounded by many anions. Each anion is surrounded by many cations. So, they're all very tightly held together. Great affection, great bonding. And that is why an ionic solid is very hard, because every cation is surrounded by a number of anions and every anion is surrounded by a number of cations, and they're all bound to each other by strong ionic attraction. Yes. That explains why they are hard. Why are they brittle? Well, that also is very, very interesting. Try to, bring a hammer, okay, and just try to beat them. Let me try that. Say, you said that fine, I have a hammer and I am going to, strike this hammer. I'm going to beat them. Fine, beat them. What happens? The moment you strike them, because they're held by strong attraction, they will not move. And by any chance, if they actually move, if you push really hard, you could move them down. And when they move down, what happens? Even if they move down slightly, you would discover that once they move down, it is cation versus cation, anion versus anion, cation versus cation, and suddenly you would discover that there is going to be a fraction. Why? Because they will repel and they will just jump away. So the entire layer will rupture. Whatever was actually attraction would suddenly turn to repulsion, and with a cracking sound, they'll just break away. Not one or two, everything will break off. Oh my God. And that is why they are brittle. So, hardness because attraction is high, and brittle because all that love turns to hate if you push them by pressure or force. Because opposite charges, instead of opposite charges, like charges come opposite to each other and they just repel away. That explains the brittleness of ionic compounds. Calculate the efficiency of packing in case of a metal crystal for a simple cubic structure. How do we do that? Well, let's draw first a lattice. A unit cell, as a matter of fact. This looks like a unit cell. And how do we draw a simple cubic structure? Let me draw this for you. What are you up to? I'm just marking midpoints so that I can draw nice, neat diagrams. Oh, this is lovely, it's very lovely. This is a unit cell for a simple cubic structure. As you can see, corners are lovingly touching each other. So edge length A is equal to 2 times R. What is the occupancy of this unit cell? There are 8 corners, 1 sphere inside. So packing efficiency is, what is the volume occupied? Volume occupied is the volume of 1 sphere. So 1 sphere 4 by 3 pi r cube divided by volume of entire cube. Entire cube is A. But A is equal to 2R. So instead of A, I could say this is 4 by 3 pi r cube divided by 2 cube r cube. Oh my God, this is pi by 6, which is 0.52 something. So 52%, only 52% is packing efficiency in the case of a simple cubic structure. What about packing efficiency in the case of body-centered cubic structure? Let's take a look. Body-centered cubic structure. Let me draw a diagram for BCC. This is most difficult and ugly looking diagram to draw because that body-centered sphere is always a very huge and enormous ugly looking entity. But well, this is the way it is. Let me make an attempt and draw this nicely. I think I'm doing a good job. Please note, all the corner atoms are actually touching the central atom. Corner atoms are touching the central atom and they may not touch each other. In fact, they would not be able to touch each other. Okay, so what does that mean? It means that if I make a section like this, if I just cut away one portion like this, can I do that? I can. And if I do that, what would I get? See, this is, if this edge is A, if this side is A, and this also is A, see, this is A, this is A, so this is A root 2. Oh wow. And what about this? This also is A. So actually, if I cut away, this is a rectangle. If I cut this away, what I have is a rectangle. I'll draw that for you. It is this. This side is A and this side is A root 2. Oh my God. And I have a huge central sphere and I have corners which are clearly and happily and lovingly touching it like this. Let me draw it in some more systematic and clean fashion. Yeah, this is what it looks like. What about the other edges? This is A root 2 and hail Pythagoras. We have this as R, R, R and R. So this violet line, a purple line is 4R, and thanks to Pythagoras, A square plus 2A square, this is diagonal, which is A root 3, and by figure this is 4R. Oh my God. So I have a relationship between edge length A and radius R. Yes. What is the occupancy of this unit cell? Well, occupancy is 2. One at the body center and one at the corners, 1/8 into 8. So if you talk about packing efficiency eta, what would be eta? Eta would be number of atoms within the cube is 2. 4 by 3 pi r cube is the volume occupied by them divided by A cube, right? And what is A cube? A is 4 by root 3R. So this is 8 by 3 pi r cube divided by 4 by root 3 R. It is cubed. Oh my God, this is such an ugly thing. If you just solve this, you have, I'll just do this for you. This is 8 by 3 pi divided by 4 cube, and cube of root 3 is 3 root 3. 3 cancels off, 8 2s are. So this is pi root 3 by 8. If you solve this, this comes out to be 0.68. So BCC has approximately 68% packing efficiency. Now we have to calculate the efficiency of packing in case of a face-centered cubic or FCC structure. How do we do that? First, let's make a unit cell. How would you draw a proper FCC structure? Draw with me. I think it will be useful. First, draw the face-centered atoms like this. Okay. And what about the corners? We will have the corners. We will not be cornered ever. Just take a look like this. Okay. Oh wow, this is what FCC looks like. Yes, my dears, this is what FCC looks like. You can shade it also in case you want to make it more prominent. Now, there are 8 corner atoms. Yes, and at each corner you get 1/8, and there are 6 faces, half each. The total occupancy is 4. Yes, that means there are 4 spheres within this FCC structure. Fine. And if I look at just this face, I could discover a few things. What? That this side is A. Yes. This side is A. Yes. So this diagonal, this fat, thick diagonal should be A root 2, right? And if you care to see, this is radius R, 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 and R. If it is vague to you, I'll just make this cleaner for you. Oh. I'm just removing the dirt so that your life becomes easier. Now can you see this? A, this is A root 2. So A root 2 is 4R, or A is 2 root 2R. A is 2 root 2R. Such a beauty. Now, efficiency packing. This is, now there are 4 spheres. So 4 into 4 by 3 pi r cube divided by A cube, which is 4 into 4 by 3 pi r cube divided by A is 2 root 2R. So 2 root 2 and cube of that, so 2 cube and cube of, so root 2 into cube will give you 2 root 2. Fine. 2 cube, 8. 8 into 2, 16. 4 4s are 16. Fanciful. This is pi by 3 root 2. You solve this. This is around 0.74. Okay, what does that mean? That means that packing efficiency of FCC structures is around 74%. And that actually is the best packing ever.